Welcome back. Now we move to chapter 11, where we will talk about time-independent perturbation theory. The first part of this chapter will be devoted to explaining the theory behind time-independent perturbation theory, and the second part will be about applying that theory to explicit examples. So I like to use I think this joke here is a pretty good example of the big problem that physicists and theoretical physicists in particular are facing. It's usually physicists are usually derided for being able to solve a very highly symmetric problem. And for example, we can understand a spherical chicken in a vacuum, as I said, this joke there. The point is that even though we spent a lot of time in chapter 9 and chapter 10 solving problem exactly, including the hydrogen atom, we found that we needed to have a fairly simplified problem to be able to do so. It turns out that most problems we are trying to solve in real life are not so simple. In fact, we lose spherical symmetry and we lose many symmetries, and we end up with a problem that's totally unsolvable using mathematical techniques as we know them. So that's the reason why we have to find a solution to be able to at least get an idea of what the solution of the Schrödinger equation is for more realistic problems. So we had to resort to these advanced mathematical tricks, and now we had to do that even though the problem we're trying to solve was fairly simple. So what happened with real world experiment is that we are stuck and we cannot solve them mathematically. So there's a reason why people came up with methods to try to have an idea of what the solution are. This is what's called perturbation theory. So this is what we are going to do now. We are going to look at non-degenerate perturbation theory. Non-degenerate perturbation theory corresponds to a theory where we are only going to focus on states that are not degenerate. In other words, it's going to be easier to calculate the effect of a perturbation on such a state that is not degenerate. In the second part, we will expand this into a degenerate state and see that the problem is slightly different in that case. In fact, we will see that the effect of perturbation, the first effect of perturbation, is to shift the degenerate state differently. So in other words, to split the degenerate state into separate state. But this is what we are going to do in section 11.2. Okay, suppose we can write the Hamiltonian this way, H0 plus H1. And H0 is the unperturbed Hamiltonian, is the largest part of the problem. And we have a perturbative Hamiltonian. Now the idea is that we can solve the eigenvalue problem for H0, but we cannot solve the eigenvalue problem for H. And we are going to build solution of the Hamiltonian H on the basis of what we know for the solution, the known solution for Hamiltonian H0. So this is what we suppose we know, is that the eigenvalue of H0 are well known and are given there by this equation on this slide. And what we need to solve is for the general wave function psi of n and the energy En without any subscript for the full Hamiltonian. That's what we want to solve. Okay, so the perturbative expansion for this will be written the following in the red box. So the idea here is that we are going to introduce a coefficient lambda. And lambda will be the same thing as the strength of the perturbation. So for example, if lambda is equal to 0, we end up with a non-perturbed problem. And if lambda is equal to 1, we have the real problem, real system with the full perturbation. So we're going to study this for lambda going to from 0 to 1. Okay, so let's see how we can do this. We are going to solve this problem by writing that the eigenstate psi n, which is therefore the eigenstate of the full Hamiltonian, we're going to write it as a Taylor expansion as a function of lambdas. Okay, and of course what we don't know is all the different states, phi n of 0, phi n 1, and so on and so forth. These are going to be the perturbation to the wave function, or to the ket in this case, and we will have to find analytical formula to see what we need to calculate. We are going to do the same thing for the energies, and for the energies we're also going to suppose that the energy can be expressed as a series of the power of lambda, and of course we hope that the series converges. Okay, so remember when we look at the ammonia molecule in the electric field, we find that the Hamiltonian in the basis 1, 2, remember the basis 1, 2 is when the nitrogen atom is either above the plane or below the plane. We found that we actually solved this problem in the presence of an electric field. The electric field, an external electric field, certainly has an effect on the energy, since there is a built-in dipole moment coming from the fact that you have a non-uniform distribution of charge between nitrogen and the plane of hydrogen. So anyways, the point is that there is an effect that actually shifts the energies. And what we found is this problem can be solved exactly. This Hamiltonian can be solved exactly, and this is what we found back when we were studying this problem. And we also said that we can write this energy as a function, or as a series as well, by expecting that the electric field that we actually bring up is much smaller than the interaction between the two states 1, 2. Okay? So in other words, we are solving this problem. We could have solved this problem for the electric field treated as a perturbation to the system that we started with. In that case, we can have a Taylor series of the square. We can express a Taylor series for the square root that there is in the exact solution for the energy. And then we found that indeed the problem ends up being a series, an infinite series of powers of mu e times e. So, in other words, we could have solved this problem using a perturbation theory, very much the same shape as what we found in the previous slide, where we said that we want the energy to be solved as a series of power, of higher and higher power of mu e times e. So we are going to substitute this the proposition for the states, for the ket, and for the energy, and we end up with this equation that looks very long, but it's actually fairly simple. On the left-hand side, we have the full Hamiltonian h0 plus lambda h1, and then we have a ket, which is really the ket psi, which is expressed as a series as a function of ket phi n and a subscript 0, 1, 2, and so on, which we don't know, right? We don't know those kets. This is what we need to calculate. And on the right-hand side, we have the same thing, and also for the energy. So the energy also is going to be expressed as a series, as energy En with a subscript I. Now, those energy subscript is, we don't know them either, so we will need to find a way to calculate them. Okay? Now, the thing is, on the left and on the right, we have lambdas and different powers of lambdas. And what we will do with this is to identify the same power of lambda on the left and on the right, and that will allow us to find us different values of h0, hn0, hn1, and so forth, but also the ket phi n0, phi n1. Okay? So let's do that. So the coefficient for each power of lambda should be equal, since lambda is arbitrary, we know that. So at the 0th order, on the left-hand side, we only have h0, phi n0, and on the right-hand side, we have en0, phi n0. So basically what it says is that at 0th order, the solution for the ket of the full system are the same as the ket of the unperturbed Hamiltonian, and the energy is the energy of the unperturbed Hamiltonian. This is not really surprising. That's simply saying that this is the exact solution when lambda is equal to 0, and we already knew that. So we suppose we can solve that problem, as we said at the beginning of this lecture. Now, at first order, we can also do the same trick on the left and on the right, we are only going to look at those states that have those coefficients, sorry, that have in first order in lambda, and we end up at h0 phi n1 on the left hand side plus h1 phi n0. Okay, so this is first order in lambda, and we have something similar on the right hand side. So that allows us to write, that allows us to find the correction phi n1 already, so which is very useful. And then we can do the same thing for second order and so on and so forth. We can keep going forever. So when we do that, of course, we end up with a series of equations that will give us more and more information about the perturbed energy, but also the perturbed state. Okay, so let's go back to first order. So in first order, we have this equation, and this is pretty straightforward. Very often students are a bit scared by this equation because of the notations, and you know, there are parentheses, there are numbers, subscript, lower script, all those sort of things. But in fact, this equation is fairly easy to apply, and in fact we are going to do that right now. This is an equation that we use most often in quantum mechanics for time independent perturbation theory. Actually, we don't use this equation as is because we are going to find a formula that can be derived directly from this equation. And this is what we are going to do in the next few minutes. So, as always, when we have an equation that involves different cats, we are going to project it on the brass. And for that, we will use the basis set that is actually the eigenstate of H0. So remember, we call them phi n 0. And so we can do the dot product on phi k0. So we end up with this equation here. By the way, the first equation we do now is for k equal n. So we're going to project the top equation that's on this slide on the phi n0. Okay, so this is what we obtain. I've not done anything yet. The only thing I've done on this equation is to move the scalar en0 and en1 outside of the bracket, which I can since these are just numbers. Okay, so remember that since H0 is a Hamiltonian, it's Hermitian, so it can be applied both on the left and on the right hand side, so either on a bra or a ket. And of course, we automatically see that the effect of H0 on the bra phi n0 is simply it's easy to calculate, since phi n0 is also an eigenstate of H0. And we remember that we have a complete basis, so that if k and n are different, then we find 0. The inner product is 0, otherwise it's equal to 1. All right, so that allows us to simplify things quite a bit. In fact, it allows us to simplify the second equation that's in the black box to the equation on the red box. And we find something that's interesting. We find that the correction to the energy to first order is nothing else than the expectation value of the perturbation Hamiltonian H1 for an eigenstate of H0. So this is what this equation means. So that's an interesting result. Think about it. You have a system that is not before the perturbation, and it lives in a stationary state, phi n0. What's the first correction you have to that energy when you turn on the expectation, when you turn on the perturbation, is to change the energy by what that state, what the energy of that state for that perturbation H1. That's really what it means. That makes sense. Of course, we know that the state is going to change because we changed the Hamiltonian, but at first order, this seems like a plausible result. Okay, so this is what we find at first order. Now, we can also look at the effect for the energy eigenstate, and this is what this slide shows. And instead of doing the inner product on phi n0, now we are going to do the inner product on phi k0, when k is different from n. Okay, so when we do that, we obtain the equation, the large equation there that we have an inner product, and of course we also know that the last term is going to, in fact I didn't even write it, the last term is going to disappear since phi k0 and phi n0 are orthogonal. Remember, these were eigenstate of H0, and what we end up with is that the projection of phi n0 the phi n1 on phi k0 is given by this equation on the right hand side of the blue arrow. So one thing, this is where students get lost, so I like to spend a few seconds to explain here. The eigenstate of H0 were written phi k with a superscript 0 in parentheses, okay? So all those terms are orthogonal to each other for all the terms that have a 0 in the superscript, okay? So that means that here on this last equation on this slide, those two states that I have, phi k0 and phi n1, they are not orthogonal. They have no reason to be orthogonal because the phi n0 is the 0th order approximation to the state, while phi n1 is the first order correction to the state. So there is no reason why they would be orthogonal. So one thing that students sometimes need to remember is the orthogonality relationship. And just to clarify this completely, this was the previous slide. What matters is this last equation that I just highlighted. So the only orthogonality relationship we know is between states that are with a superscript 0. Okay, so this is what we end up with, and we find that indeed we can actually find the amplitude, the probability amplitude of finding the state phi n1 on the basis phi k0, which is great because that means that we can express the state of the full Hamiltonian on the basis on phi k0. And this is one of the coefficients that we find, one of the coefficients that we need to calculate. Okay, so this is the equation. Of course, n has to be equal to k, n has to be different from k, which makes sense because if k it was equal to n, we already have that correction basically, since we know that the 0th order, this is the one that corresponds to k equal n. Okay. So this next equation simply expresses the correction to first order phi n1 on the basis on phi k0, which is an orthogonal basis since these are the eigenstate of H0, and we just found that this particular equation can be written this way, where we have highlighted the part of k equal n and the part of k equals 0. Okay, so we don't have much trouble with the right-hand side, the rightmost part of this equation, since we just calculated those terms, the probability amplitude phi k0, phi n1. Now the first part there is a little bit more painful to calculate, it turns out, and this is what we are going to do now. In fact, I can already tell you what's going to happen is that the first term is going to cancel, it's going to disappear. And we will see why in just a second here. Okay, so when k is equal to n, to calculate this expression, we have to remember that the full state has to be orthogonal. And if we use this Taylor expression of the full psi n in terms of phi n0 and so on and so forth, and phi n1 and so on, we end up with that equation that we have right there. Okay, so we see the next term will be in lambda square and so on and so forth, and we also know that phi n0 is properly normalized, so the first term is equal to 1. Okay, so that means that all the other terms have to be equal to 0. So in other words, we must have that the probability amplitude phi n0, phi n1 has to be a pure imaginary number, because we are going, the terms on the previous slide shows that we have lambda times a number plus lambda times the same number, complex conjugate. So that term has to be a pure imaginary number. In fact, we are going to show now that it is to be equal to 0. So we're going to do it now. So we can write, now that we have decided that phi n0 and the probability amplitude phi n0, phi n1 is equal to IA, we are going to replace this expression in the full expression for psi of n. And remember, we have at first order phi n0. In first order, we have phi n0 times IA lambda. We just said that IA was the probability amplitude for the first term, and then we don't touch the other terms. And we can see that these two terms are actually the first two terms are the first two terms of the complex exponential e to the power IA lambda. What happens is that what we see, this is equivalent to having a complete an overall phase factor. So we can decide to use a phase factor of A equals 0. In other words, psi n and phi n0 start with the same phase, if you will. That's one way to look at it. In other words, we have A equals 0, and the first term phi n0, phi n1 is equal to 0. Okay, so that's a little bit of the complicated part of this equation. Another way to look at it is simply to say that the portion of the full ket that is projected on phi n0 has already been taken care of at the 0th order. Therefore, we don't further correct that particular state. That's the reason why A equals to 0. That's another way to look at it. When all is said and done, we end up with this equation, which is probably the only equation you need to know for this part. Just remember the sketch of how to calculate to get this equation. But this is a very important equation because it tells you how the state change upon a perturbation. This is a change in first order. Okay? So if lambda is very small, it's a pretty good approximation. Now let's have a look at second order. Sometimes in second order we have a little bit more changes. So second order, remember, go back a few slides to see the second order. This equation came from simply equaling the terms in lambda square from the full equation we had using the perturbative approach, and we end up with this equation, which is start to be a little bit heavier. And if you kept going on the orders of perturbation, correction for the perturbation, you will find that you have more and more terms. But remember that we have calculated many of them already. We know phi n1, we know en1, we know phi n1, we know phi n0. So we know a lot of them. In fact, the only two we don't know is phi n2 and en2. So this is all that we need. And of course, we are going to use the usual trick. We are going to project this equation on the bra phi k. In fact, we're going to start by projecting on phi n0, just shown in the red box there. Now, here is what's interesting with this, is that the first term, of course, we know how to calculate it, but we know that we are going to find that the en2 will be equal to phi n0 h1 phi n1. How do we see that? Well, we see that because the first term on both sides of the previous equation are the same, right? Since h0, phi n0, sorry, is also an eigenstate of phi of h0 for en0. So these two terms will cancel. Second, the second term on the right-hand side of the equation also cancels, because remember, we have spent quite a bit of time showing that phi n0 and phi n1 are orthogonal to each other. This is what we just did in the previous slide when we said that A was equal to 0. So that allows me to calculate En1 as the second order correction to the energy. We can obtain that by calculating the matrix element between the unperturbed states and the first order perturbation correction. So this is what that equation says. And we of course also remember what the phi n1 actually was. So we can of course now use the identity operator on the phi n0 basis, and we end up with a correction to the energy that's obtained by the product of two matrix elements. And then you see from this equation, of course, already, that's a second order correction, because you have twice h1, so h1 square, if you will, that is going to play a role in the calculation of the second order correction to the energy. Okay, and of course you find that this h1 square is obtained by this, by remembering that H1 is Hermitian, and we have a number times the complex conjugate, and of course we have this. And we can see even better that it's a second order correction. We are not going to calculate the correction to the state because it's a little bit painful, but I invite you to do it if you want. Usually we are happy to stop at first order. That doesn't mean that there are not quantum mechanical problems where we actually need to worry about them, but we are not going to worry about them in this course. The point is that this slide summarizes everything we've done. We know the correction to zero order, first order, and second order for the energy values, and also for the states at the first order, zeroth order, and first order. Okay, now it's time to move to the degenerate perturbative theory. So far we have looked at states that only have a non-degenerate solution, so we didn't have to worry so much about dividing by zeros, essentially. So now this is something that we have to worry about a little bit because, of course, if we have states that are degenerated, we can no longer use the formula we had previously where we divided by the energy minus the energy of the unperturbed state. So these things is going to become very clear, hopefully, after this presentation. Okay, so remember, this is the correction we had right there in first order for the energy. And clearly, in fact, this is not for the energy, this is the correction for the state itself, right? So, of course, we know that this diverges for degenerate state because we were saved by the fact that n was different from k in that first equation on the top left. But if we have a degenerate state, of course, that means that there will be some k's that are different from n, where En is equal to Ek. This is the definition of degeneracy. So we are going to, instead, we are going to work in what's called the subset of state that are degenerate. So we are going to work in this subspace, the subspace which has a size n, capital N, where all the state phi n comma I are the states that have the same energy. So this is the subspace, the degenerate subspace of a given energy. So the question now, of course, we know that any linear combination of those states could be used as a basis for my Hamiltonian, since in fact they will have the same energy. So a linear combination of them would still be an eigenstate of the Hamiltonian. So the main question that we are going to try to solve is which linear combination of those states should be used for the perturbative system, for the perturbed system. So this is what the perturbation basically, so the way to think about it, the perturbation H1 is going to impose, at least to some extent, is going to impose which linear combination I can use of those states to be an approximate solution of my full Hamiltonian. Okay, so before we turn on the perturbation, we could use any combination of those states within a subspace of same energy. Now, the point is the perturbation lifts a little bit that degeneracy. Not only it imposes a specific linear combination, but also gives the value of the energy splitting. So basically the difference, how the energies are changed. Okay, so we are going to write again new state, which is psi n. So the nth state for the perturbed system. We are going to write it as a linear combination of the states that are part of the subspace, so phi n comma I of 0, plus some corrections, lambda, phi n1, and so on and so forth. So as opposed to what we were doing before, this zeroth order correction to the problem is now a linear combination of the degenerate states for that given energy. So we don't know what the CIs are. We just know that we can use a combination of them. And then what we are going to see now is that turning on the perturbation will actually give you the value, what values of CIs you should use. Okay, so now if all the CIs are different, so from C1 to Cn within the subspace of degeneracy, if they're all different, then that means that we completely leave the degeneracy. It could so happen that some CIs will be the same still. That means that we do not completely leave the degeneracy. So let's see what's happening. Well, we can actually substitute that eigenstate that we don't know we're looking for, psi of n, in the Schrödinger equation of h0 plus h1 times the equation, and so on and so forth. And we find at first we find that at first order that we have this equation right there. So that's what we're interested in. And then if we project that equation on the phi n j, so we are going to project actually we're not going to project on, we're going to project on any particular state phi n j, which is part of the subspace of the degenerate energy. And we are going to end up with this equation we have there. And how we go from the equation in the center of the slide to the last equation, to the equation at the bottom of the slide, is by remembering that when I project with phi and j, we see that the first term on both sides of the equal sign, so the first term, they do cancel, right? Because phi and j 0 is an eigenstate of the Hamiltonian H0 for energy En 0. Okay, so we can do that, and when we do that, we end up with the equation that we have right there. And we also remember that, of course, phi and j 0 and phi and I 0 are also orthogonal. So remember those phi and j, and again, the main issue we have here is really an issue of notation. So please take time, pause the screencast and make sure you understand the notation. The notation is not complicated, it's just a little bit cumbersome. There's nothing complicated. So in any case, so when I project phi and j and phi and I both at 0th order, that means that I'm actually projecting two states that correspond to the same energy En 0. But if the two states are different, they're going to be orthogonal, even in the subspace, obviously. There's a reason why this probability amplitude is equal to the Kronecker delta Ji. Okay, so we end up with that equation, which you can rewrite here in the box. And what we see really is, by now you should recognize something, I hope. You see, this is an eigenvalue problem. In fact, you can rewrite this in a matrix form, right? So the left-hand side of this equation is simply saying that we have a matrix, so the representation of H1 in the subspace of the energy En 0 times a vector of CIs is equal on the right-hand side to a number En1 times the same vector. This is an eigenvalue problem that can be written like this. So again, this is one of those things that you get familiar with by doing it. So try to convince yourself that indeed the equation that we have in the box can be rewritten in a matrix form as written right there. Okay, so it's time to think a little bit about what we have here. What we have actually an eigenvalue problem, an eigenstate problem as well. And if I can solve this problem, I find the CIs and also the En1. So what I find is that all the En are going to give me the correction to the energy, and all the CIs will provide me the acceptable linear combination of this eigenstate that were initially degenerate. They will give me new values of those of this particular combination that correspond to the first order correction due to the perturbation H1. So the big difficulty when we solve this problem, of course, I think it's clear, is going to be to calculate the matrix element H1, 1, 1, and so on and so forth. So this is something that we do. We calculate those elements on the basis of the unperturbed Hamiltonian. And if we can do that, then we can solve the entire problem, and then we find a solution at first order. So that's what the perturbation, the degenerate perturbation theory is all about. So the summary for non-degenerate state, I already showed you this slide a couple of times. We can calculate things at zero order, first order, second order. Here I'm not showing the second order correction to the eigenstate, but only to the energy. But for the degenerate state, we end up with this equation that, as I just explained to you, which is actually a matrix, an eigenvalue problem, and we only work here on first order. There exist, of course, second order and third order and so on and so forth methods to calculate perturbation, effect on perturbation that are larger, at a higher order, but we're not going to worry about those now because we can already solve quite a few problems with this. The main thing here, and this is a theme that comes across very often in quantum mechanics at any level, even the high level, is the fact that, that we have a perturbation. The perturbation lifts the degeneracy. Remember that we have seen that degeneracy usually comes from the existence of a symmetry, sometimes a hidden symmetry or accidental symmetry, but it usually comes from a symmetry. Now, if the symmetry is broken by the perturbation, then clearly the degeneracy has to be lifted. And this is exactly the mathematical machinery that's going to give you this lift in degeneracy. So this is really formal. This is formalizing something that makes a lot of sense, of course. Okay, so the problem. Diagonalizing the matrix is easy. The hard part is to calculate the matrix elements, because sometimes the subspace is pretty large. Remember, the degeneracy for the hydrogen atom is n squared, where n is the principal quantum number. So if you look at n equal 3, you already have a 9 by 9 matrix. So that's start to be a lot, because 9 by 9, it's 81 matrix elements. I know this is Hermitian, so we only have to calculate a little bit more than half of them, but still, it's a lot of calculation. So we can actually use a few tricks, and this is what we are going to do in the second part of the screencast, really use a number of tricks that will allow us to calculate those matrix elements. Okay, so we can start now by looking at an application, and the application is the Stark effect in hydrogen. So the Stark effect is a very interesting problem that has been solved early on for hydrogen. The idea is to place hydrogen atom in an electric field. So there is an external electric field, E, and we know an electric field will interact with a charge or will interact with a dipole. And in fact, we know the interaction between a dipole and the electric field. The energy of a dipole in the electric field is given by mu E dot E, where mu E is a dipole moment. It's a vector. The vector is actually connecting the charges. So here we're going to suppose the charge is E. So we have a dipole between a proton and an electron. This is, of course, classical description. And we know that the energy is going to be minus mu E times dot E. In other words, this interaction leads the dipole moment to be parallel to the electric field, right? Because when it's parallel, then the dot product is maximal. So, in other words, it's a negative contribution. In other words, it reduces the total energy, which is more stable. It's exactly what we want. The dipole moment is, as I said, given by minus E R, where R is the position operator. So this is how we see that the perturbation Hamiltonian H1 is indeed an operator. In fact, it's even a Hermitian operator, because, as you know, R is a Hermitian operator. The dipole will point from the electron to the proton, just like we always do. And so the point is what's happening when I turn off an electric field and what's happening to the state. So remember that early on hydrogen atom was extremely studied because this is one that we could solve, a problem that we could solve exactly quantum mechanically. So the idea was really to test quantum mechanics on hydrogen atom, and placing the hydrogen atom in electric field was a good idea because we can also look at the effect of that. So let's see what's happening. But before we start, let's not forget that we are trying to do physics, and we don't want to end up with a situation where we just do mathematics. So before we start, let's think about the problem we are trying to solve. We have a spherical, so in a ground state, we have a spherical distribution of a charge around another charge, around a proton. So clearly the dipole moment, the average dipole moment in the ground state should certainly be zero, right? You have as many charge at every, you just have an equivalent number of probability of finding charge anywhere on the sphere, therefore the total dipole moment is zero. Therefore you do not expect that that you will have a very large change in the energy, certainly not in the ground state, okay? In the ground state of the Hamiltonian without electric field. Now, as you have an electric field, clearly the charges are going to move around, and you have a polarization of your electric shell. So in other words, electrons will be more likely to be found somewhere along the line of the electric field, and you are going to create a dipole moment. So it is the effect of the electric field that creates a dipole moment, and that dipole moment will then interact with the electric field. So you see that this is a second order effect in the electric field, right? The dipole moment that's created, that's induced by electric field, depends on the electric field, which leads to an interaction with the electric field. So it's an E-square effect. So in principle, I expect, even without doing any calculation whatsoever, that the ground state energy in first order should not be changed compared to the 0th order, right? But on the other hand, it should be changed to second order. So that's what I think should happen, okay? Now, let's try to see if mathematically it makes sense. Hopefully it makes sense. If it doesn't, that maybe we can learn something. But I think in this case it's going to make sense. Okay, so remember the Hamiltonian for the hydrogen atom is given by this very simple Hamiltonian, which is actually looks simple, but it's not that simple to solve, as you remember. You have a kinetic energy, and then you have an attraction between the proton and the electron. Let's not forget that we are working in the center of mass, in the reference frame of the center of mass. Mu is the reduced mass of the electron, very close to the mass of the electron, but not quite exactly. And we found that the eigenstate can be labeled N, L, and M, N being the principal quantum number, L being the angular momentum, orbital angular momentum, and M being the projection of that momentum on the z-axis. Okay? Good. So let's try to see what happens. We are going to suppose the field is along z. The main reason why we like that is because we will suppose also that the projection, so mh bar, will also be along z. That will make our life a little bit easier. You will see. So if it's along z, we end up with h1 being z, right? Of course, this is the R operator just along z with the dot product. And we can look at the non-degenerate state first. So we are going to look at the ground state. Good. So the ground state at first order, remember, it's always the same thing we say. We have to calculate the expectation value of the operator for the ground state. This is exactly what's written there. The ground state is n equal 1, L equals 0, and M equals 0. And we have to calculate the matrix element for the z operator. And obviously we find that this value is equal to 0 because the eigenstate that particular eigenstate has a definite parity. The fact that it has a definite parity of -1 to the power L, so in this case it's L equals 0, so it's an even. So the point is, because it has an even parity, there is as many plus z and minus z contribution to the integral, and you find equal to 0 as expected. So at first order there is no correction, as I said, simply because what it says is that there is no dipole moment in the ground state of the hydrogen atom without electric field. Okay, that's not a really big surprise. Now on second order we have to calculate this kind of integral, this kind of, when I say integral I really mean that's the same thing. People use integral, but the integral is the same thing as the matrix element. This is because the matrix element is really an integral. And we have to calculate the integral between the NLM state and the ground state 1, 0, 0. Okay, so we have to calculate this. And so when we calculate this, we'll see that this is not equal to 0 because electric field induces a dipole moment. And in fact, we can calculate this effect, and I've not provided the value, but the point is, you see that at second order, you have a perturbation to the energy. So this is all good. Now, what's really exciting to do is to look at the degenerate state. And so we are going to do a degenerate state. We're going to use the first excited state with n equal 2, so principal quantum number n equal 2. We know that we have a number of states there. We have L equals 0 and L equal 1. And then when L equals 0, m can only be equal to 0. When L equal 1, m can be equal to -1, 0 or +1. So I'm sorry, there is a mistake on this slide. It should be -1, 0 and +1. Okay, and of course that means that we have all those states that are possible. Actually, we have 4 states. Remember this degeneracy n square. We calculated in chapter 10. So the 4 states are of course all n equals 2, and we have those L equals 0 and m equals 0, L equal 1, m equals 0, L equal 1, m equal 1, L equal 1, m equal -1. Now, remember we are in the degenerate state. We need to build that matrix, which has the matrix elements are just all the possibility, all the combination between those 4 states for H1. So we end up with a 4x4 matrix that we need to diagonalize. There are different ways to calculate this matrix. One way is to brute force, just go ahead and calculate the whole thing. That's possible, it takes forever, but it's possible. The other one is to, in fact, think a little bit. And thinking is always a good thing to do. So we are going to use that second part. Okay, so first of all, if a bra and a ket have the same value of L, they have the same parity and therefore vanish for this perturbation. Okay, what does that mean? Well, we know that the parity of the states is -1 to the power L. This is what we did when we look at the spherical harmonics. And if the same value of L means the same parity, and since we're integrating, H1 is really proportional to the operator Z, then if we have the same parity, that means that we are integrating an even function times an odd function. Well, the integral is 0, clearly. So all those terms where L are the same will be 0. And that's quite a few. In fact, it's all those are 0. Many of them. More. All these will be equal to 0. The integral is equal to 0, right? Good. That's excellent. So, of course, H1 is invariant about the z-axis. We know that. In fact, H1 is invariant about the z-axis since the electric field is along the z-axis, and the Hamiltonian commute with the corresponding generator of rotation Lz. We know that, of course, because we can rotate the whole system around the z-axis, and it's not going to change anything since electric field is aligned with the z-axis for a system that was initially spherically symmetric. Okay. So now let's have a look at the other system here, the other states where the L and L prime are different, right? Because if if they have the same value of else, then of course we know that we have an even function, therefore they disappeared. It was the blue boxes on the previous slide. Okay, so we know that H1 and LZ commute, so let's use that. Okay, we know that since they do commute, M prime H bar times the bracket on the top left there, we can introduce M prime H bar inside, right? And replace M prime H bar by LZ. Okay, so this is a good place maybe to stop the screencast and convince yourself of this equal sign there. Remember, LZ is Hermitian, so it can certainly be applied on to the bra on the left. Maybe it's easier to go from the right to the left. You see directly how you go from the right to the left. Okay, good. So we have this. We also know that LZ and Z commute. Therefore, this is certainly true. How do I know that Z and LZ commute? Well, because clearly they must commute, and also because H1 and LZ do commute, clearly. So now I can apply LZ to the ket NLM, and I obtain MH bar. Of course, MH bar being a number, I can bring it out of this matrix element. And so I find that M prime H bar times a number is equal to MH bar times the same number. So clearly, the only way this can be true is that if the term is equal to 0, unless M is equal to M prime. So when M is different from M prime, this matrix element should be equal to 0. Okay. So that removes also all those red boxes, because in those terms, M and M prime are different. Therefore, the matrix element has to be equal to 0. So I end up with only 2 matrix elements, and of course, they are complex conjugate of one another, so I really only have 1 to calculate. So you see, we started from 16 elements, and we end up with just 1 to calculate, which is much simpler than the brute force approach. So this is the one we need to calculate, and it is not equal to 0. In fact, the way to calculate it is to remember that the states 2, 0, 0 and 2, 1, 0 can be expressed in terms of the spherical harmonics and the radial function r and r prime. And we end up with this equation in spherical coordinates, which we can calculate, and I am not providing the proof here. This ends up being a calculation that's involving some integral that we can find in tables. The point is that we realize that this integral is actually minus 3a0, all right? a0 being the Bohr's radius. So you end up with this Hamiltonian matrix. Remember, that matrix is the H1 representation. This is the H1 matrix in the representation of the basis of the degenerate basis function for the first excited state of the hydrogen atom. So that's the reason why we have a 4x4. So we have to diagonalize that matrix, which is fairly trivial. We find that 2 eigenvalues are going to be equal to 0. So that's interesting. This means that those 2 particular eigenstates are not going to be perturbed by the presence of the electric field. And then we have 2 states, two energies that are either going to be shifted up or shifted down. So this is very interesting, of course, because that means that we do have a split of the four-fold degenerated states that we started with. Now we're going to end up with a 2-fold degenerate state with the same energy as before, then one that's stabilized, and what this is actually excited, so increased in energy. That's what we end up with. Okay, and then we found, of course, we can understand why we have those eigenstates. Those eigenstates are obtained by a combination of the eigenstate we started with, because not only we have the eigenvalues, we also have the coefficient Ci's, which are the eigenstate of that matrix. Now let's move to another example of the application of the time-independent perturbation theory. We are going to apply it also to the hydrogen atom, and we are going to see that even though we thought that we solved the hydrogen atom exactly, it turns out that we made a number of approximations, which makes it so that, in fact, if you measure with high precision the spectrum of hydrogen atom, you do not exactly find what we calculated. And this is what we are going to do in this section. In fact, most of the corrections that we are going to look at now are due to relativity, to special relativity effect. It comes from the fact that the speed of the electron can get very high. In fact, it can get a fraction of the speed of light, which means that in reality the equation we should use is Dirac equation and not so much Schrödinger equation. But it turns out that the effect of this high speed of the electron in its orbital can be treated in a perturbative manner. So this is what we are going to do in this section. So the corrections that we are going to do are going to lead to the fine structure of the hydrogen atom. So remember that we already spoke about the hyperfine structure of the hydrogen atom in chapter 5, where we had the interaction between the spin of the nucleus and the spin of the electron. So we had a spin-spin interaction S1.S2, and this is a very small effect because both spins are small, correspond to small magnetic moment and small magnetic field that interact with one another, and it's called a hyperfine splitting, and we'll talk about that again. This is different. This one is not related to spin-spin interaction. In fact, it is related to the relativistic correction to the Hamiltonian, and this is what we are going to study right now for hydrogen. Okay, so there are actually three effects that we have for the relativistic corrections, and I'll talk about them in details. The first one is simply the correction of the electron's kinetic energy. The fact that the electron gets so high speed forces, in fact, the p squared over 2m to be an approximation to the kinetic energy. As you know, the mass should also depend on the momentum, which we have not done so far. The second thing is the spin-orbit interaction. There is an interaction between the spin of the electron and the orbital angular momentum, and I'm going to tell you a little bit where it comes from and the effect. And then finally, we will bring up the Darwin term, which is a correction to the corrections. We will see that there is something missing, and this is what the Darwin term does. Let's start with the correction to the electron kinetic energy. Okay, so the full kinetic energy, of course, in a non-relativistic expression will be the kinetic energy of the electrons plus the kinetic energy of the proton. This is what's given there. And in reality, the relativistic expression, and we are not going to do relativity for the proton because it cannot be accelerated to a speed that's very close to the speed of light in these conditions, but instead here the electron can because of its small mass. We can write things this way, the way that's written on the slide, and we can of course rearrange things a little bit like this, and we find that we can use a Taylor series expansion of the correct relativistic expression and find that at 0th order the kinetic energy is indeed p squared over 2m, but in fact we have to reduce that term by a pe to the power 4 over 8 m cubed c squared for the electron, plus other terms. But in any case, we find that there is a correction to the kinetic energy that we can apply due to the fact that the electron is almost relativistic, is relativistic. In fact, the relativistic corrections are even more important in heavy atoms because there is so much charge that the electrons that are so closer to the nucleus can actually acquire even larger speed, and so the relativistic corrections are even more important here. In fact, this is the reason why some metals are not silver looking. For example, gold has a golden color, which is actually due to a relativistic effect. But we are not going to talk about that in this screencast. Instead, we're going to see what's the effect on the correction of the energy using the PE square, PE to the power 4, in fact, as a perturbation to the Hamiltonian. So this is my kinetic energy in the center of mass frame. We have not replaced the second mass ME by a mu because essentially ME cube is very much the same anyways, because the mass of the electron is so much smaller than the mass of the proton. So we have the usual H0. We have seen it so many times for the hydrogen-like hydrogenoid atom. And what we need to do is to calculate the effect of P to the power 4. But before we go there, we just remember something useful, which is related to the virial theorem, which I provide here without a proof, is that for an eigenstate of the Hamiltonian, so NLM, P square over 2u, so the expectation value is actually minus the value of the energy. This is the virial theorem, and of course, if you look at the expectation value of the potential energy, is twice the energy En0. Okay, this is something you've seen in theoretical mechanics, and this is actually also true for the expectation values of the operators in quantum mechanics. Okay, so that allows me to have an idea of what P square over 2 mu is. And you know where we are going with this, obviously. Okay. We get this energy that depends on n, and of course, if n is very small, this effect is much larger, since we have 1 over n squared, just as we expect. And that's also related to the fact that the electron is farther away or closer to the nucleus, so the acceleration depends on this. Okay, so we find that the kinetic energy, we just know that the kinetic, the correction to the kinetic energy can be written as a perturbation that I'm going to write HK, and it's obtained by this expression that we obtained from the previous slide, which was simply the first order correction to the kinetic energy due to the relativistic effect. And we're going to treat it as a perturbation. Okay? So this is the term we need to do as a perturbation. Of course, this term is still rotationally invariant. Of course, since we have only the P square, which is real distance. So HK still commute with all the component of the vector operator L. No problem with that. That means that the eigenstate of H0, which are highly degenerated as a function of n, of course, so the matrix representation of the Hamiltonian will also be diagonal. Indeed, all the eigenstate of HK are also eigenstate of L. That's the point, right? Now, we are going to look at the degenerate perturbation theory. So we are what the idea of that is to look at the representation of HK in the basis of the Hamiltonian we started with. But the Hamiltonian you started with has eigenstate that are also eigenstate of L. So in other words, the eigenstate of L are the same as the eigenstate of H0, which are the same as the eigenstate of HK, since HK and L commute. So that means, in other words, that the perturbation theory here shows that the Hamiltonian, the matrix representation, will be a diagonal. So, in other words, all I need to do is to calculate the diagonal element of that perturbation, which obtained, for example, by this expression. Now, this is the expression we need to calculate. We are going to remember, obviously, and this is just a small manipulation, that the PE square over 8m cubed c square can be rewritten so that we highlight P square over 2m square. And then we know that P square over 2m square is the Hamiltonian we started with, H0 plus ZE square over R. You know, this is just coming from the definition of H0. There's nothing really crazy here. But the advantage, of course, is that we rewrote So we re-express the perturbation as being the square of two operators that I know much about. That allows me to calculate the perturbation, so the expectation value of p square over 8m cubed c square, using those two operators that I can calculate easily, the product of two operators. I end up with this expression here. And then we can calculate this, and I'm not doing it in this slide. The point is that it's becoming just simply doing more integral in spherical coordinates. The point is we find a kinetic energy correction that's obtained as shown in the box. So there is indeed a correction to the energies that's going to depend on n and on L. So the larger the value of n, the less perturbation we have. This is clear since it goes as n over n, 1 over n4 and n over n cubed. But for small values of n, we expect this correction to be fairly large. So this is, for example, for a 1s state, we expect this correction to be fairly large indeed. Okay, so let's try to see now another relativistic effect, which is spin-orbit coupling. Now, for this, I'm going to use an argument just to try to convince you why they should be disturbed. We always use the rest frame of the proton. Or in fact, we use the rest frame of the center of mass, which is almost coincides with the proton, just because of the mass of the proton is so much higher than the mass of the electron. Suppose for a second that we are sitting on the electron. So as the electron is moving around the proton, okay, right, in a classical way, it's the same as from the point of view of the electron to see the proton moving at the velocity of the opposite velocity. In other words, the electron sees a charge moving around it. So in other words, it experiences an electric current. Okay? This electric current, of course, produces a magnetic field. This is what Biot-Savart establishes, and that equation there gives you classically what the magnetic field is for a charge that's actually with velocity v, which is v cross r, that's non-zero. That's what we have right there. So we find that there is a magnetic field. In other words, this little idea of using different relativistic point of view shows that this is the same as the electron experiencing a magnetic field due to the movement of the proton from that perspective. Now, at the same time, the electron has an intrinsic spin, which is the intrinsic spin angular momentum S, and which means that there is an associated magnetic moment. So that means that there is a magnetic moment that can interact with a magnetic field. The magnetic field comes from the orbital angular momentum, while the magnetic moment comes from the spin angular momentum. So in other words, when everything is said and done, when we wrote all the equations together, we do expect that the interaction between the two will be an S dot L, S being the spin, L being the angular momentum. Okay, so being the orbital angular momentum. So this is what we find. This is from a classical treatment of this. This is mostly to show you the origin of this effect, right? It's purely a relativistic effect. It comes from the fact that it depends on which frame we are working in. So this is what I was explaining here, and also, of course, the magnetic field are inherently relativistic, as you have done in electromagnetic theory. The presence of, you can interchange a magnetic field and an electric field depending on the point of view that you're working with. Okay. Well, it turns out there is a factor of 2, so this classical treatment is fine. It's mostly fine. But if you do it really correctly, in other words, with the Dirac equation, you would find there is a factor of 2 missing if we do it properly, quantum mechanically and not just classically. And it means that the spin-orbit coupling is actually given by what Biot-Savart gave us, but with a factor 1/2 in front of it. But the point remains that the perturbation to the Hamiltonian is an L dot S term. Okay. So this L dot S is a little bit cumbersome to work with, but we are going to do it here. I'm going to sketch the description of this L dot S. So let's try to keep focused on this. It's going to be a little bit heavy duty at place, but we're going to make it together. All right. Okay. So we have a state now where we have to explicitly give the spin plus z or minus z. So far, there is no term in the Hamiltonian that involves the spin. So we didn't have to worry about it. We just said that we have a spin there, so the electron is either spin up, spin down, but there was no spin dependent operator. Now there is one, so we have to explicitly give the spin. So we are going to suppose that we have a general eigenstate of the angular momentum, Lm plus z or Lm minus z, which is a direct product between an eigenstate of L and an eigenstate of S. That can be written just as written in the slide there. So if Lm for the L operator and 1/2 1/2 or 1/2 1/2 or 1/2 1 minus 1/2, which are both eigenstates of the S operator, depending on the projection, plus 1/2 or minus 1/2. We know that L and S commute because they do actually act on different degrees of freedom of my system, so they certainly do commute. And we can create states that will be eigenstate of L square and Lz, S square and Sz. So now the thing is, we need to create those states. And the way that things are usually done is by looking at the total angular momentum operator J being equal to L plus S. This would be my total angular momentum operator J equal L plus S. So if you are a little bit lost with this, try to go back to chapter 5, where we in fact had two spin angular momentum S1 and S2, and we combine them together for we have a S operator that was equal to S1 plus S2. This is essentially the same thing here. We are combining an angular momentum coming from orbital and angular momentum coming from spin. They do operate on different degrees of freedom. So remember the definition we had using direct product. But at the end of the day, we can certainly do the same thing here. And this is what we are going to the solution we're going to sketch right here. So we now need to diagonalize L dot S the same way we diagonalize S1 dot S2 for the hyperfine correction to the Hamiltonian that we've seen before. Now we remember that J square can be written as L square plus S square plus 2LS. Remember, J is equal to L plus S. Here, we don't have to worry about L dot S being different from S dot L, since L and S commute. And Jz is Lz plus Sz. So this is the projection on Z. So we know that Jz has to commute with L dot S. Why? Because Jz commutes with L square, certainly, right? Lz commute with L square, that we know, and Sz commute with S square. So the fact that Lz commute with L square and Sz commute with S square is not an issue, and the fact that Jz commute with L square becomes directly apparent from the discussion that we can have now. So in other words, now we can write 2L dot S is equal to J square minus L square minus S square. So we find that indeed Jz commutes with L dot S. So just to convince yourself that Jz indeed commute with L dot S, and again, the only difficult part really here was to show that Jz was commuting with L square. We can write it this way. Jz is equal to Lz plus Sz. and then we can replace L dot S by its expression, which is Lx as x plus Ly as y plus Sz, Lz as z. Then we end up with the commutator that we know well, like Lz, Lx, Lz, Ly, Sz, Sx, and Sz, Sy. And it turns out that all the terms cancel out. And when we cancel out, that means that Jz does commute with Ls. So that's the reason why we see that Jz commutes with L square. L square, J square minus L square minus S square. This is what it means. Okay, so this is very interesting because that means that if we can use eigenstate of Jz, we also find eigenstate of Ls. Okay, very good. So in hydrogen atom, there are two n squared degenerate states for each n. Okay, so far, including in this screencast, I spoke about n square. But the reality is that we have 2n squared because we have spin up and spin down. So far, we didn't have to worry about the spins. But it's now, since we have the spin orbit coupling, we certainly have to include the spins. So what we just found is that the commutation relationship between Jz and L dot S means that only state with the same eigenvalue of Jz can be mixed together by their perturbation. So this is something that's very important. Since Jz and Ls commute, the only way that a matrix element involving Jz can be non-zero, because if the states were different, we would automatically find with the Kronecker delta, we would find that the matrix element would be equal to 0. Indeed, if we have an eigenstate of Jz, that means automatically the eigenvalue can be taken out of the matrix element, and we end up with a normalization condition that we have to fulfill. So, because the spin orbit Hamiltonian commute with L square, we can then focus on state with the same values, the value of L. So again, HSO commute with, so hydrogens for spin orbit commute with L square, and if it commutes with L square, that means that the states, the matrix elements, must have the same value of L for the same reason as what's written in the boldface text up there. Okay. So if we take one particular value of L, there are just two states that are eigenvalues of Jz equal to m plus 1/2 h bar. So m plus 1/2 is basically the eigenvalue corresponding to Lz plus Sz, right? So that would be only the possibilities that we have. So the best way is to do this. So if we have those two states, Lm and plus z and Lm plus 1 and minus z, those two states have the same Jz. That's what all this means, right? Because the Jz is Lz plus mz, and in the first case, this is 1 plus 1/2, it's 3/2. In the second case, Lz is m plus 1 minus 1/2, so we end up with minus m plus 1/2. So in both cases, we have m plus 1/2 and m plus 1/2. So that's very good, because that means that we for any value of L, unless L equal 1, the only possible state that we have are m plus z and m plus 1 minus z, for which the matrix element of Jz will be different from 0. Okay? Because otherwise we would automatically find that the states are orthogonal to each other. So when m equal to L, of course, we cannot write this, because if m equal to L, we cannot use the second state. The second state is impossible because the maximum value of m is, of course, plus L. So the second state is not possible. So if we have the case m equal L, then we cannot do this. In other words, the matrix element will actually also disappear. So the question we can ask ourselves is what combinations of the two states are eigenstate of 2L.S? And once we have those combination of the two states, then we can automatically calculate the matrix element. Okay, so this is what we've been doing. So remember now, we go back to the idea of L.S expressed in terms of the raising and lowering operators. This result, you may not remember this result, but this is a result we actually worked out in details for S1.S2. So go back to chapter 5 to memorize, to remember how we calculated this. And we are going to have a shorthand notation when the first state is Lm plus z and the second state is Lm plus 1 minus z. And we are going to calculate the matrix element for those states. And then we find that when we do that, we can calculate the matrix elements using those operator, raising and lowering operator, and we end up with that matrix right there, which we can orthogonalize. So we can diagonalize, sorry, not orthogonalize, but diagonalize. And when we diagonalize it, we find eigenvalues that will tell me how the different states are shifted due to the calculation of the interaction between the orbit and the spin. And then we find that two possible eigenstates are L equal L, lambda equal L, and lambda equal minus L plus 1. Okay? And so we can calculate the eigenvalues of J square, since we know the eigenvalues of 2Lz, and the value of eigenvalues of J square, we can calculate it from the fact that the eigenstate of Ls are also eigenstate of L square and S square, and then we can find that the different values of J square are L plus 1/2 and L minus 1/2. Okay, so this is a total spin, if you will, the total angular momentum, if you will, that includes both the spin and the orbital part. And we can calculate the eigenstate as well. So this is a little bit cumbersome. What I just explained to you in 2 slides, and frankly in less details than I would like to give you. This is really a sketch that's usually detailed in a full lecture. So we probably would need 2 hours to present how to calculate the 2LS. This is not the kind of thing that we could ask that I would ask in an exam, but this is something that you should probably understand how it's going. Okay, that's really what matters. So, of course, the shift in energy is given by the expectation value of the Hamiltonian for the state that diagonalize the perturbative Hamiltonian. So we have the different change, and then we can calculate, we can find out that at the end of the day, what really matters is to calculate the expectation value of 1 over r cubed, okay, for the different state NL. And this result is given to you without any proof. We find the spin-orbit coupling. So the interaction between spin and orbit is given by those expressions. So there is going to be a shift downward for the low value of J and a shift upward for a high value of J. That's what we find. So that means that for the atom, the notation should include not so much the value of L or the value of S, but really the value of J, which is the good quantum number to consider, which is the total angular momentum, J. Okay? So the first one is 1/2. It's easy. It's 1s 1/2. It's easy because you're combining L equals 0 and S equal 1/2. And the other states, you are combining L equal 1 and S equal 1/2, so you can have 1/2, 1/2, 3/2. So the first 1/2 comes from the combination of L equals 0 and S equal 1/2. And the second 2 terms come from L equal 0, L equal 1, S equal minus 1/2, and L equal 1, S equal 1/2. So that's how you get 3/2. And the proper state, of course, are given by this, just as I explained now. Excuse me. Now the Darwin term, where it turns out that the spin-orbit coupling is given by this. Now, this is purely mathematical, and this is where we actually sometimes forget a little bit about the physics. It turns out that what's surprising here is that those terms are non-zero even when L equal to 0. So the question, how can you have a spin-orbit coupling if there is no orbital momentum, orbital angular momentum? Yet this term shows you that you do. So clearly something is missing. In fact, something is missing that would actually cancel those terms when L equals 0, right? I mean, you cannot have interaction between a spin and an orbit if the total orbital angular momentum is 0, and yet these equations don't seem to indicate this. So what's going on? Well, we can actually, this is where Darwin came up. So Darwin is from Charles Darwin family. It's a nephew or something like that. So it's apparently they were all very smart. The point is that if we use the full Dirac equation, we would find that there is an additional relativistic term that would cancel those L terms. And this Dirac term, this Darwin term, sorry, is actually obtained by this operator, which is now an operator which is commutator between the P operator and another commutator between P and V. We are obviously not going to do this here, but the point is what we find is that we can find the correction due to Darwin only for those states that are non-zero at the origin. And remember, the only one that cannot be non-zero at the origin is L equals 0. You have to remember that from chapter 9 that we find that the radial part of the equation was behaving as r to the power L. And of course, this is only 0 when L equal to 0. This is only non-zero when L equal to 0. And everything, then when you put everything together, we end up with the hydrogen atom, and we have all those terms. So when we add the kinetic correction, the spin orbit correction in Darwin term, we end up with this nice description that no longer depends directly on L. So if L equals 0, we are saved. And we have the corrections, which are about 10 to the minus 5, and this is called the fine structure. So these corrections lift the degeneracy because we have the relativistic effect. And we end up with those lines that can be measured experimentally. And this is actually proven, this has been demonstrated experimentally on this fine structure of the hydrogen atom. There's no dependence on L. Which is very interesting because each term, all three terms depend on L, but the sum of them do not. There is an additional Lamb shift that's known to, that's going to lift the degeneracy too, the additional degeneracy, the fact that the two different value of L's would have different corrections. So the relativistic correction does not show a dependence on L, but the Lamb shift will actually take care of this correction. Which is even further, we'd even have to go into further details in the theory in quantum electrodynamics, where even the interactions are quantized. So this is where we would need to be, but this would include an additional shift, which is called a Lamb shift. Okay. And of course, just to be complete, we have to add the hyperfine structure that we have already established in chapter 5 due to the interaction between the spin angular momentum of the proton and the spin angular momentum of the electron. And again, the Lamb shift and the fine structure are actually fairly comparable. I mean, it's not exactly the same, but they would also be, there's an order of magnitude difference. But the point is, we can also measure these experimentally these days. Okay. Now it's time to move to the next and final step of this screencast, and this is going to be about the Zeeman effect in hydrogen. So I'm only going to give you a very quick sketch of how to solve for the Zeeman effect in hydrogen. Zeeman effect in hydrogen correspond to applying a magnetic field to the hydrogen atom and see what's the effect on the spectrum of the hydrogen atom. And it can also be solved using perturbation theory. So the effect of external magnetic field is like this. You have to remember the interaction between an external magnetic field and a magnetic moment mu is given by minus mu dot B. Now the point is that the total magnetic moment of the hydrogen atom has two parts. It has a part that's related to the angular orbital momentum, and the other one that's related to the spin angular momentum. So you will notice the factor of 2 that's missing comes from the fact that we have a spin 1/2. And then we also shows the factor of 2 difference. It also corresponds to the fact that we really have two origins for the angular momentum. One is orbital, kind of classical, and the other one is purely quantum mechanical. So we end up with an operator that's well described as S and B. And we know that we have to actually act upon the spectrum of the hydrogen atom where we have all the effect of spin, for instance, just like we did in the previous section, through the spin orbit coupling, in the fine structure and the hyperfine structure. So the Hamiltonian can be written like this. So the Zeeman Hamiltonian, coming from the fact that we have a magnetic field, can be written this way. And we can actually look at what's happening in the states, for example, in a degenerate state. So what we are going to do in the next two slides, and I'm going to give you a very, very short outline of how we solve this problem for n equal 2, and when the hydrogen includes the spin orbit coupling. So that means that J can either be 3/2 or 1/2. We have done that before. Why is J 3/2 and 1/2? Remember that for n equal 2, L can only be equal to 0 or 1. And when you combine 0 with 1/2, you can only have 1/2. This is for J, total angular momentum. And if you combine L equal 1 to plus 1/2 and minus 1/2, you can only have the 3/2 right there. This is what we've done in the previous slide. So we end up with this Hamiltonian to diagonalize, essentially, right? And this is something we can do by rewriting the Hamiltonian using Jz plus Sz. Same difference. Remember, Jz is Lz plus Sz. And this Hamiltonian commutes with both Jz and L square, as we have already established. So that means that states that have different mj cannot be mixed together. Again, indeed, if they have different mj, that means that the states, the matrix element of those states, between those states in the operator HB will be equal to 0, right? Just because the states will be also eigenstate of HB, since they are eigenstate of L square and Jz. So in other words, we need to have states that have different values of mj. Okay, so we have different ways to do this. In particular, we can write this equation, and if we remember how to express the different states in terms of the states for simply using the eigenstate of Lz and L square and dot for S square, instead of using the eigenstate of Jz like it's written right there, we end up with an expectation value for Sz, so which is just one part of the correction to the energy, which can be obtained by this calculation. And again, this is a place where I invite you to stop the screencast and try to figure it out. The point here is not so much to go in the details of the calculations. I mean, this is very important to do in general, but for this particular case, I want mostly to insist on the fact that you have to be concerned by the total angular momentum, not just by the spin part or the angular part. And when you do that, when you do properly the calculations, you obtain that the expectation value of Sz is plus or minus mj h bar divided by 2L plus 1. And then, of course, getting the expectation value of Jz is much simpler, and you obtain a correction to the energy that's obtained by the equation in the red box. And this is a correction to the energies of the n equal 2 state, and that for a magnetic field B. And you see that these corrections depend on depends on mj, but also on L, which again makes sense if we have this total magnetic total orbital angular momentum, total angular momentum J, as well as the angular momentum L. And then we found that in fact for any states we find that the correction is a function of J, the total angular momentum, and L, the orbital angular momentum, and we usually call this function the Landé G factor, that can be measured for different state of the hydrogen atom, and then we can use that to determine the different states of the hydrogen atom. This is how it works. Again, this is mostly algebraic manipulations. The point is that how to get started for solving such a problem is to get the proper operator for the Hamiltonian, and remember that you have to look at the total angular momentum. So I'd like to thank you for paying attention to the screencast. The screencast can be essentially divided in two parts. The first part is where I describe to you the perturbation theory for non-degenerate state and for degenerate state, so in both cases for the time-independent perturbation theory. And on the second part, we started to look at a number of examples. We look at Stark effect. There is an expectation that you should be able to reproduce a Stark effect and understand a Stark effect from perturbation theory for both degenerate and non-degenerate state. And after that, I spent some time illustrating how we can do perturbation theory to describe the Zeeman effect, but also to describe the relativistic correction to the hydrogen atom, and that led to the fine structure of the hydrogen atom. I do realize that this screencast went pretty fast on the mathematical description of the fine structure as well as for the Zeeman effect. So there is no expectation that you should be able to understand every details of these last two aspects just based on these slides, but I hope that you can at least understand the sketch of the proofs that we described in this screencast.